Welcome to This Explainer. Today, we're diving right into Grade 7 Physical Science, specifically focusing on the core of Unit 1, Lesson 9. We're going to walk step by step through a real investigation to see exactly how forces affect motion. We aren't just going to sit back and read about science today. Nope, we are actually going to model how to plan a simple forces investigation, record observations and data, identify patterns, and write a rock-solid claim evidence reasoning explanation.
So we've all been there, right? You know from everyday life that a heavy box is tough to push. You've definitely felt it if you've ever tried to slide a loaded bookshelf across a carpet versus moving an empty one. But today, we're stepping into the shoes of true scientists. We have to ask ourselves, how do we actually prove that a heavier object is harder to move? I mean, it's not enough to just say it feels heavier. We need hard empirical evidence.
To get that evidence, here is our roadmap for the explainer. We'll be hitting planning a forces investigation, gathering and organizing data, spotting patterns in motion, the CER explanation framework, and finally, evidence versus unsupported opinions.
All right, let's jump right into Section 1, Planning a Forces Investigation.
Okay, to set up an investigation that actually meets those physical science standards, you really have to follow 3 crucial steps. First up, you have to identify your variables. Basically, figure out exactly what you're going to change and what you're going to measure. Second, gather your tools. Think force meters, standard weights, and the actual boxes you'll be pushing. And third, plan your measurements. You have to decide exactly how you'll record the change in motion so that someone else, literally anyone, could come along and repeat your exact steps.
In this lab walkthrough, you are the lead investigator. You're running the show. So to make this a truly fair test, you decide that the mass of the boxes will be your independent variable. That's the factor you intentionally change. You know, swapping out a light box for a medium one and then a really heavy one. Meanwhile, the distance they travel after a specific push, that's going to be your dependent variable. It's exactly what you're measuring to see if your change actually had an effect.
Which brings us to Section 2, Gathering and Organizing Data.
Now, before we even think about pushing those boxes, remember this absolutely key scientific rule. To share your findings with the rest of the world, all positions, forces, and motions must be described using a shared reference frame and specific standard units. We can't just measure distance in something like footsteps or force in super hard shoves. No way. We have to use specific units like newtons for force, kilograms for mass, and meters for distance.
Let's look at the actual numbers from the relationship we're testing. We applied exactly 10 newtons of force to each box. We kept that force constant to guarantee a fair test. Well, when we pushed the 5-kilogram box, it moved a solid 2 meters. But then we doubled the mass to 10 kilograms, and it only moved 1 meter. Doubling it again to a hefty 20 kilograms, it barely made it 0.5 meters. This data right here clearly shows how the mass of the object totally changes the distance it travels.
Moving right along to Section 3, Spotting Patterns in Motion.
When you plot out that data, the cause and effect relationship is just undeniable. It's unmistakable. As the mass increases, the distance drops dramatically. It forms this perfect, predictable downward staircase pattern.
And just like that, your data proved some core rules of physics. First, the total sum of forces on an object absolutely determines its change in motion. Second, a heavier mass demands a much greater force if you want to get the exact same movement. And finally, just as we literally just saw in the lab, if you use a constant given force, like our trusty 10 newtons, a larger mass is inevitably going to travel a shorter distance.
Okay, on to Section 4, the CER explanation framework.
CER. It stands for Claim, Evidence, and Reasoning. Any strong scientific argument has to start with a claim. Now, this isn't a guess, it's not a hypothesis. It's a clear, concluding statement that directly answers your original investigation question. So, for our lab, your claim would just simply and directly state whether a heavier object is harder to move based on what you just discovered.
Next up is evidence. You can't just make a claim and expect everyone to take your word for it, right? You gotta bring the receipts. This is where you pull those exact numbers straight out of your data table to back up what you just claimed. You wouldn't just say, oh, the heavy box didn't move very far. You'd say, the 20-kilogram box only moved 0.5 meters, using specific kilograms, newtons, and meters. That is exactly what separates true scientific evidence from just a casual observation. Finally, we hit reasoning. Honestly, this is usually the trickiest part, but it's where the real science happens. This is where you put on your detective hat. You have to provide the logical justification that links your evidence right back to your claim. You do that by explaining the established scientific rules of forces and mass, proving exactly why the data you collected supports the answer you provided.
For this particular investigation, your main detective rulebook relies heavily on this foundational principle from the NGSS core ideas. The motion of an object is determined by the sum of the forces acting on it. If the total force on the object is not zero, its motion will change. By integrating that rule into your reasoning, you connect your specific little box-pushing experiment to the massive universal laws of physics. Pretty cool, right?
Almost at the finish line. Section 5, Evidence versus Unsupported Opinions. Let's put this into perspective with a quick comparison. Think about someone saying, the box was way too heavy to push and it barely moved at all. That is an unsupported opinion. It's just a personal feeling. What exactly is too heavy? What does barely moved actually mean? It's entirely subjective. Compare that to saying, when 10 newtons of force was applied, the 10-kilogram box only moved 1 meter, compared to 2 meters for the 5-kilogram box. See the difference? That statement uses specific variables and measurements. It empirically proves the point.
So, the huge takeaway from this explainer is this. True science relies on logical connections between precise data and explanations. Scientific knowledge is fundamentally based on empirical evidence. And that means using specific numbers and standard units, and clearly comparing your independent and dependent variables. If you ever find yourself using vague words like fast, heavy, or hard, you're slipping into opinion territory. Always stick to the data.
Well, you've officially modeled how to plan a simple forces investigation, record data, find the patterns, and write a rigorous CER explanation. Now that you've got this process down, I wanted to leave you with a provocative thought for your next lab. Based on the proportional relationships we just saw today, if you wanted that massive 20-kilogram box to travel the full 2 meters, just like the 5-kilogram box managed to do, how much force do you think you'd need to apply? Think about the math there and keep investigating.